summary. I put these slides together this morning because I didn't have internet in my hotel last night. So just a quick summary of things we discussed last week. You can actually go to this link here, which has the link to the talks, the introduction talk from last week, as a follow-up talk on some topics that were discussed, and today's talk at this link that's on the agenda. So I've pulled my summary slide from the beginning of last week to just give you a quick overview of things that were discussed. So one aspect of reinterpretation and interpretations of run-to analyses in terms of BSM physics, of course, comes from these direct BSM searches. One aspect that was discussed there was assessing model independence in those measurements, and also difficulties in the workflow for reinterpretation of these, going from issues in detector simulation if you're going beyond the bounds of where the detector simulation is being validated, also how you work out the standard model rates that contribute to your RICO level search, and validation to do with these two topics. Simplified likelihoods, which has been discussed in the statistics working group, is an approach to get around a lot of these problems in the reinterpretation. One big aspect that I discussed last week was that standard model, well, I should put this always in quotes, standard model process cross-section measurements are already widely used for reinterpretation. You can see some examples in my slides from last week of various different types of reinterpretations that have been done with various standard model measurements, where, as we discussed, the model dependence then is included in the systematics on modeling. So these are in the data systematics, or they should be. One thing to allow the standard model cross-section measurements to be reused for reinterpretation is making sure that all the relevant data on the data measurement and also auxiliary material supporting that is provided in HEP data in a consistent way, and this is something we've been discussing with the stats working group about the presentation of covariance matrices, how you split that, also whether you should provide signed up and down shifts and so on to cross-correlate between different measurements. Going beyond just standard model process cross-section measurements then, I also discussed how you can potentially extend this concept to unfolded generalized searches for new phenomena, such as in MET plus JETS, where you don't have a specific standard model process in mind you're hoping to measure, but you're trying to measure some processes which are sensitive to new phenomena, but otherwise applying the same unfolded cross-section measurement procedure to that. So one thing that was discussed last week, but I'm still interested on more input on this, is the use cases of such data. Are there any particular final states that are interesting to be unfolded for reinterpretation beyond the ones I already discussed last week? And then there are statistical questions related to this, such as what happens when you try to unfold in the limit of no data, no standard model process, or no BSM expected. This is something we haven't really tackled so far. And also just the limitations of this procedure and where you run into model dependence, independence problems. All of this then moves towards then a sort of global picture that we would like to get to of LHC beyond the standard model limits, where we'd like to get into a situation where we could combine dedicated beyond the standard model searches with standard model cross-section measurements really in a single picture. So we'd like to make our standard model cross-section measurements, like to make our direct, dedicated, high sensitivity searches, maybe generalized searches, and combine all of these to make the best picture we have of anomalies in LHC data. How do we best make use of these standard model measurements, and are there any measurements missing that we might find if we get to the stage of performing this kind of global picture of LHC limits? And how do we figure out which measurements are missing? Something that was also discussed last week, which I'll come back to later in the talk. How we characterize our input to such a global picture also matters. We have simplified models to tell us, we can search for any anomalies we like, but then how do we characterize whether that anomaly can be linked with another anomaly in some other measurement? We have to have some model perhaps in mind to do that. Simplified models, neural nets to figure out where the deviations are. Are there any other approaches? And can we approach basically some kind of LHC simplified likelihood perhaps to tell us that, this global picture? And one thing that I mentioned but we didn't really discuss so far, but have somebody is interested, is in the potential future use of CMS and Atlas Open Data. So far, the LHC experiments have released a small amount of data for educational purposes, but this has also been used in the case of CMS for standard model measurements by external people. Could we extend this in future to releasing some data that could be used for reinterpretation? What are the needs to do this? What potential use cases, what data would you be interested in seeing? And is there any potential interest? Because I don't think this will happen without any actual pressure from external world. So the first thing I'll discuss then is the reinterpreting standard model measurements as BSM searches. This is kind of where we left off from one of our parallel meetings last week. 3 topics that were discussed in that meeting. The first was one thing we would like to do, we identified we would like to do, although we haven't made any progress on it yet, is we'd like to do a comparison of how simplified likelihoods do for reinterpretation versus unfolded cross-section measurements, how they compare against each other, and how they compare against dedicated RICO level searches. If you have a benchmark in mind where you can apply each of these 3 criteria, can you figure out if one does better than the other? Is one always preferred, or are there regions of phase space where you run into problems, edge cases, when you do one versus the other? How much sensitivity is actually lost in the reinterpretation procedure, and is that significant? So if we provide these standard model cross-sections for reinterpretation, are you always so much better off doing RICO level searches you shouldn't even bother reinterpreting, or do you get 95% of the way to your search sensitivity most of the time? And balancing that, how much you lose in the unfolding or in the simplified likelihoods, how much do you possibly gain, on the other hand, from being able to simply combine one measurement with another in the simplified likelihood or the particle level as well, is something we want to quantify and look into a bit further. So using standard model measurements for BSM searches, we discussed last week existing uses of standard model cross-section measurements. There are, like I say, a variety of them. It just flashed up in my talk from last week, you can see on the agenda. And we also discussed how these standard model cross-sections are defined and the technical procedures to get to them, and then the limitations that come with those. And we also discussed testing a specific case of BSM model that had a lepton plus met plus jet final state and a met plus jet final state as 2 possible final states from one particular model. So I can't remember who's here who was looking into that, but one thing we discussed was potentially using 2 particle level standard model cross-section measurements, which are W plus jets and met plus jets, differential cross-sections shown here, that could be used potentially to set limits on this BSM model in these 2 final states correlating the information between the 2 channels. So one thing that's already arisen from feedback I've got, but people in the room trying to do this, is that a really critical thing to aid reinterpretation, even at the particle level cross-section measurements level, is providing the standard model predictions of the process being measured along with the data and HEP data. That's not always the case. So for this older W plus jets measurement, for example, the data and the correlation information is in HEP data, but not the standard model prediction, the best standard model prediction we have of W plus jets. For the MET plus jets, which is newer, we do have a standard model prediction, which you can swap in and out, but it's nice to have it there to aid with reinterpretation. So I don't know if anyone in the room wants to update us on any progress or difficulties they've had so far in this. I think this is still ongoing, of course. If not, then perhaps we can discuss it at the end or raise your hand. So this was just the workflow we discussed to do this reinterpretation of the standard model cross-section measurements. Basically, you have your standard model prediction either given or generated by yourself. You have your BSM model. You stick it into the provided rivet code, compares against the data with some statistical analysis, taking into account the correlations, and then you pop out with your reinterpretation at the other end, performing your favorite statistical hypothesis test. So really the only input you should have to provide is the BSM model and some statistical analysis on the back end. So it's using the existing tools, this is relatively easy to get started with, I think, although people who have been doing this the past week should comment. So one thing we've also discussed is in these unfolded cross-section measurements in simplified likelihoods, we of course take into account correlation, well, to get the best sensitivity, we take into account correlations between bins of measured distributions. But one thing we have a problem in doing, and are likely to have a problem for the foreseeable future, is how to handle correlations between two different measurements that might be published at different times using different calibration of the data and so on. So even things that you might assume are correlated between two analyses from experimental systematics such as luminosity, if those measurements were done in different data-taking periods, you can't necessarily assume these two systematics vary coherently. And if you don't know the proper correlations, you have a chance of getting the reinterpretation wrong. Both you can exclude a point that shouldn't be excluded, or you can not end up not excluding a point that you should be excluding. So you can gain and lose sensitivity inappropriately. This is not a problem within an analysis, reinterpreting a single analysis, but the power we'd like to aim for is to combine lots of LHC measurements, and this is an issue about the unknown cross-correlations. You could solve this by, of course, publishing all analyses or multiple analyses coherently from Atlas or CMS, but this takes a level of coordination that I don't think is going to be ever possible. So how do we get around this problem? One thought that was just put up, discussed at the end of last week, was that we can, of course, just brute force test a variety of correlation scenarios between one bin in a differential distribution in the W plus jets analysis and one bin in the differential distribution of the Met plus jets analysis. Assume full, no, or anti-correlation, and anything in between, and scan over the parameter space that we're setting limits on, and take the most conservative. That is going to reduce your model dependence. Reduce your model sensitivity a lot. Quantifying this, you have to do this for every single model, but at least you don't run into the problem of excluding a point inappropriately in your parameter space. But this is really the first discussion we had on this topic. I don't know if there are other thoughts from the experimental side or the reinterpretation side about how we can deal with this. Then a couple of slides about some other topics that were raised. So statistical aspects of reinterpretation. Wolfgang mentioned to us about the possible use of these generative adversarial machines, a model builder and a reinterpreter, experimenter, reinterpreter, who fight against each other essentially to try and find the best analysis you can perform and models that fit that analysis. So there's been a little toy study done that shows this performs very well using RICO level search procedures and data. One thing that Wolfgang mentioned at the end of his talk is it would be interesting to potentially extend this to include standard model reinterpretations, standard model measurements and the reinterpretations of those in such a network. So I'd send you to his talk to look at more details about this. Two other topics that were on the wiki page, which I haven't heard personally any update about, but are being discussed, and perhaps people involved can mention something in the session if they want to, is about there's some interest in looking at these exclusive production modes for linked to future colliders. That was discussed. I don't know if there's anything further on that, but you can mention at the end. And also interference contributions between standard model and BSM processes. Some links there. There was a talk by Jeremy. I don't know if there's anything further to discuss on this topic. So that's kind of where we were. A summary of what's been discussed so far. So I wanted to ask if there's any questions on the slide so far, any input on updates since what I've written here, or anything further that people would like to discuss on this kind of reinterpretations and interpretations of standard model cross sections, or anything else about reinterpreting data for new physics in LHC Run 2 that we're going to discuss this week. Nope. Okay. Sorry? Yeah, of course, yeah. I mean, we can discuss in the coffee breaks, and then we can have, I mean, the usual plan was that we would just set up sort of informal working groups throughout the week to discuss any aspect of these topics with small groups of people who are actually interested in them, and then feed this back before the end of the week in the summary session. Okay.
Very similar to what Darren did, just a short recap of what was discussed last week and sort of what we settled on, and we are planning to work on this week, but we are totally open for new suggestions. So if you guys want to propose new ideas or new topics, we can definitely include them. Maybe today it's a full day, but maybe tomorrow we can have a short meeting just to really allow the newcomers to give new input or new ideas. So let me just, I won't go, so these slides are on the wiki. I'll show quickly. I just want to go to the last one, which is just a rough summary. Okay. Yeah. So we tried to classify some of these new signatures or new ideas into this plot. This is just a quick summary or attempt of a summary or overview in this plane. So this is decay length and multiplicity. And some of the new signatures that we talked about last week were some searches for resonances that are still not looked for. So in this prompt low multiplicity corner, we have some finite states that appear in leptoquark models that still do not have dedicated searches for. For instance, jet plus taus, leptons plus tops. One open question that we sort of thought about last week but did not went further is if we can use some of the standard model measurements to constrain these finite states. I think this is an exercise that we did not pursue, but maybe we could try it this week. Then moving to low multiplicities but longer lifetimes, we have some signatures like displaced tops. We really did not go into this. So what we ended settling on was something like emerging jets. I will give some more details about what we've discussed. And yeah, there are some other things that are not here that I'll talk about. So I will just try to follow the wiki. And so you can easily access it if you go to topics and working groups, and then there is a link for proposal for new searches. And we try to put everything that was discussed in the wiki. So if you want more details, you can go there. Meeting by meeting, we have some short discussion of the topics covered. And so this was the blackboard. This is a bad resolution picture, but some of the ideas that were listed on the second day of the workshop. So there are emerging jets, semi-visible jets here, leptons inside fat jets. I think this did not go further. Non-standard neutrino interactions, we had some discussions on that. Higgs inflation, I really do not know like if there were any further discussion on this. I guess not. Displaced vertices and broad resonances were some other of the discussed topics. So just below this, we have links for each of the main topics discussed. We have dedicated sessions for these three, I guess. Broad resonances, I think it's more or less dead by now. Okay, so we may discuss these two. I think emerging jets is the one that went maybe a little bit further. So I'll go through it first. And the main idea we came up with is okay, badly summarized on this blackboard. It's a little bit messy, but the idea is, in principle, you can have your dark sector, your hidden valley sector that's linked to the standard model through a heavy mediator. Here we are thinking about a Z prime. And for now, we assume that the Z prime is leptophobic. So it mostly couples to the standard model quarks and a copy or a image of these standard model quarks in the dark sector. For now, we assume just one flavor to make it simple. Okay. So the idea is, so the Z prime can be produced through the coupling with the standard model and then decay into dark quarks. These dark quarks are somewhat light, below the confinement scale in this setup. So they will shower, hadronize, form dark pions. These dark pions will decay back to the standard model through the same Z prime diagram, but the other way around now. So these dark pions decay back to standard model quarks. And the signature is displaced vertices. So the dark pions, they are neutral under standard model charges or gauge group. So what you see is basically a whole bunch of displaced vertices, and this is the whole emerging jets idea. In the original paper, the setup was a little bit different. They had bifundamentals being produced here, so they also had prompt jets. So the idea we are trying to look more into is how the usual Z prime searches change if you have a significant branching ratio into this dark sector. Right? So if it decays 100% to, if it has large couplings to the standard model and weak couplings to the dark sector, then you sort of move towards a dijet search for Z prime. But as you increase the Z prime coupling to the dark sector, you start to get more and more emerging jets. And our first idea was to see, okay, how these things evolve from a pure dijet search for Z prime to an emerging jet search. Like, do the constraints on the Z prime couplings and mass degrade, or they are actually stronger if you use emerging jets? What happens? So this was the main question we were trying to answer. So for that, we have set up some tasks that are ongoing. I mean, we tried to define some toy model, a very simple version where you have basic parameters, the Z prime mass, it's coupling to the standard model, it's coupling to the dark sector. Then in the dark sector, we have some parameters that for now we just assume are fixed, some reasonable values. And then the overall idea was, okay, first we need to set up the tools to compute whatever we need for this model. Most of these tools are there already. We had to do very little. So Pythia has a hidden valley implementation, has dark shower. Like it does the dark shower for you, hadronization, and so on. So the most complicated part is there already. Then it's a matter of defining a Z prime model with these new dark quarks and running it through the usual chain, MadGraph, Pythia, and so on. So this is, I think, almost there. or should be there. We have a Dropbox folder with these files and everything we need to generate events for this model. The second task was, okay, to look at usual displaced jets or displaced jet searches and see what their constraints are, how poorly they do in this scenario. This is not exactly a displaced jet because you have several dark pions decaying, so you have fewer tracks per displaced vertex, and they are all clustered together, so the efficiencies might be low for these standard displaced jet searches. So I was in charge of this. I started to look at all the searches. Actually, there are already searches for a Z prime decay into dark pions. We just need to look more careful into it. And on the other end, how the usual Z prime digest searches perform. If you do not have prompt jets, is that an issue? That's not an issue. What is the quality criteria for these jets? Do they kill? The emerging jets are killed by this criteria or not? So this is ongoing. We have some people involved here. Not all of them are in this list. We have some more people contributing. So we definitely have more meetings throughout the week to gather everything we have found so far. Everyone is welcome to join. So this is one of the ongoing projects. If we go back, another topic that was discussed, it was non-standard neutrino interactions. Let's see if I can open it here. Yeah. So yeah, few people interested in it. One of the main topics discussed is if we have an NSI operator, non-standard interaction for neutrinos. I don't know if it's easy to see, but this is for fermion operator, neutrino-neutrino, fermion-fermion. So some of the topics is how to constrain it at colliders. I think that there are already some published work on this. Another topic that we discussed a lot is how to generate this operator without generating a corresponding operator to charged leptons. In principle, by SU2 invariance, you would expect that this guy comes along with a operator for charged leptons, and that is highly constrained. Right? This is way more constrained than this operator. So, and then we had some discussion. Some of the points raised is that we can have actually dimension 8 operators that after electric symmetry breaking will generate only a dimension 6 to the neutral components of the lepton doublet, while the charged component remain a dimension 8 operator. And this is some of the ideas of the UV completion that could generate this guy. So we have quarks here playing the role of these fermions. And we have, in this setup, we have right-handed neutrinos that couple to the Z prime. And then you have a usual lepton, standard model lepton doublet, right-handed neutrino Higgs. And this guy here can generate this operator. At the same time avoid an operator for the charged leptons. So I think this is still somewhat ongoing. We did not have much more discussion about this, but we'll probably have something during this week. If you have any input, it's welcome. I think Sheng may have some new ideas to add to this. And yeah, so I think these are the main issues discussed last week. Some of the other topics, I think started and died already. These are the ongoing ones, I would say. There are also some new ideas coming up. So everyone is free to come up with completely new topics or add new input to these ones. We'll try to schedule something for tomorrow, like maybe a short but open session so people can contribute with new ideas. And then also dedicated meetings for these ongoing projects. So that's, yeah. In which case? In the emerging jet or here? The Z prime in the emerging jet case? Or here? Yeah. So at this point, no, these are not, I would say, yeah, at this point these are toy models. We don't have a specific U1 in mind. I know there will be issues with anomalies for some of these suggestions. So this is also something we're looking into. Yeah. It's not trivial, right, as far as I understand. Yeah. So we do, that's one of the tasks, to look how feasible it is to have this leptophobic Z prime, or if we can really suppress the couplings to leptons, or how much. Yeah. I mean, I know this is more or less well known, but we are looking, yeah, once you add couplings to the dark sector, if in principle something could change or not. In our setup, probably not, because they don't carry standard model charges. But yeah, that's something we are looking into as well. So yeah. Yeah, we have that was some discussion as well. So okay, it's more involved than that. This is not okay. So these are. We had this discussion. Whatever you make here, it will be proportional to neutrino masses. There is no way around it. There is one way around it, which is to make this right-handed heavy neutrinos Dirac. So you add a Dirac mass to it. Yeah, we can maybe discuss further, but. Well, it contributes. It contributes. Well, yeah. I mean, this is one of the terms of the mass matrix, right? You can, yeah. Then one, yeah. So I think you can do, if I'm not wrong, maybe Sheng discuss it with more detail, but you can do a sort of inverse seesaw here, and yeah. So you have this term, but you have direct masses to these guys as well, and I think in the end you can decouple these two things. Yeah, we can go over it. Yeah, I mean Sheng sort of motivated, but we went through this for a while. Yeah, it's not 100% sure how we can do it. Another, yeah, okay. There are other suggestions instead of using this diagram to use something else. Okay, that won't have this issue, but yeah, it's something. It was something that was discussed. We can maybe discuss. I mean, Sheng has a better idea about it, I think. Yeah, Tahan. Yeah. Yeah, I don't know. I would refer to Sheng, who proposed this thing. Mhm. 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 Sure, that would be. Mhm. 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 Yeah, yeah. So maybe. Mhm. Sure. Okay. Yeah, I think maybe as far as I remember, one of okay. So the charged lepton operator would be usually more constrained than this guy. This guy is probably easier to hide. Mhm. Yeah. Okay. We can go over it for sure. I think that yeah, one of the points is yeah, we know that the charged operator has to be somewhat suppressed. Could this one be large and have effects in other places that the charged lepton wouldn't give you something? But of course, we can go through it and yeah, think some more about the motivations, or maybe there's interesting stuff to be done with the charged lepton, and for sure, yeah. So this is good. We can already have a starting point for the discussion tomorrow. More questions? No. Okay. Thank you.